going to present a work that has already been published, and it's a collaborative work that was done together with Vivian Saint-Pagano and Michael Gill. And while at UCLA and ENS. So this is a much more practical work applied on a case study. And since I'm trained on physics and mathematics, I will probably have a different view to things that involve also economics and climate impact on it. So, and yeah, as Tim already mentioned, the title or the subject that I'm gonna present you is interannual climate variability on a very on the agriculture sector in the Sahel region. Okay, just a few words about the outline of this talk, about the structure. First, I'm gonna spend a few words on the peculiarities of the Sahel region. And I want to talk about what kind of climate indicators and economic indicators we took into account in this case study. Then in the second part, or in a very brief part, I want to talk a little bit about the methodological, because this is quite known in maybe climate science and well established. It's less known still in economics, although we already introduced it and got some interesting results. And then it's most of the part I will spend on the main results, especially on the variability in the agriculture sector in the Sahel region, and also on the rainfall and temperature, and what is most interesting in the coupled climate economic dynamics. So on the left, you can see a map of the North Africa and the countries that are involved in this study. So the Sahel region is a special region because it is under big also climate pressure, because it's a semi-arid climate. That means the rainfall is only focused on a very few, if not just 1 month in the summer, in boreal summer. And the region is situated between the Sahara Desert in the north and the subtropical savanna in the south. On the left map, you see the average rainfall in a typical January, and on the right map in August. And you see that there is a big difference in the rainfall properties in this region during winter and summer. On the right, you can clearly see that there's a band of rainfall, the rain belt, and this rain belt means moves north and south during the year. So that means those countries, they only get rainfall in a few months. Otherwise, they are completely dry. And therefore, the precipitation variability is a very important key climatic factor in this agriculture, especially in the semi-arid regions, and it, of course, then entails the increased risk in such regions that if climate changes, if the properties changes. So we can essentially divide this into different kinds of rainfall exposure. On the right, you see a low, intermediate, or high rainfall exposure, depending if the country is more to the north or more to the south. If it's very far in the north, it's really just 1 month where you get a little bit of rain and also very low rainfall level, whereas the likelihood on the south is much higher that you get rain. And although this region is, you term it Sahel region, it is not just a single entity, it is a very diverse region with strong contrasts between different countries, and that's what I would like to show you in this case study. Next, I'm going to show you the data that we are working on. we're actually working on annual data for about like 60 years for each of the countries. And on the left, you can see the annual rainfall records. This is actually average, like since you have plenty of months without rain, and just 1 month, the annual average is extremely low. But you can see again countries on the left with a high rainfall level, an intermediate, and a very low rainfall level. And what is comes very clearly out in this figure is that there's strong year-to-year variability superimposed on some long-term trend or long-term behavior. And that's what we're especially interested in. What is the dynamics of it? On the other hand, on the right side, you see the corresponding temperature records, average. And here you will see, beside a long-term trend, you again see some strong year-to-year variability, but it looks less spread, less diverse in temperature than in rainfall. On the other hand, we also then wanted to compare those dynamics with economic indicators, of course, standard indicator, the GDP. But not only this, because we're especially interested in the agriculture, we also studied the agriculture value added, which you see on the right. On the left, there's not a very surprisingly new picture here. There's a really strong persistent growth in it, and very little year-to-year variability, and it explains an extremely small part of the variance, less than 2%, around the trend estimate, which is in red, and the data in black. On the right, on the other hand, you see that agriculture has much stronger fluctuations around the trend estimate, and it can even go up to, like in the case of Senegal, it can go up to 20% those fluctuations. So we had therefore the question, okay, if we see those strong year-to-year variabilities in the agriculture, what is behind those dynamics? Is this maybe, can we find a fingerprint or an imprint of the climate key factors that are in this region play an important role? One problem in this region is the lack of irrigation or other technologies that would help stabilize agriculture. That means agriculture is totally dependent on the precipitation, and therefore we observe a strong variability in those agriculture data. And therefore we ask, is there a potential link between variability we observe in the climate and in the agriculture? What is also very important in this region, that agriculture has a very high share on the GDP. It can go up to 50%, but it's typically around 30%. So it is an important economic factor in this region. So the next 2 slides, I just want to give a very brief overview of the decomposition and statistical test, because if you see something in the data, we cannot just say, okay, it looks reasonable, we also need a hypothesis. So the tool, the favorite tool of choice here is a singular spectrum analysis. It is already well known in the dynamical system analysis or in geoscience in general. But up to now, it's only has very little entered the economics, econometrics especially. If you are not familiar with this method, you might be maybe familiar with principal component analysis. This method is somewhat linked to it, but it does not only consider spatial correlations, but it also considers spatial and temporal correlation, which is very important for us to decompose data into trends and long-term trends, into cyclical parts and residuals. And this is therefore our favorite method of choice for the detection of coupled dynamical behavior. Because when you study such extremely complex systems, each of it is already extremely complex, the climate and the economic system, you cannot expect that both systems are just correlate. We don't get something like a correlation coefficient of 0.1 or 0.08 or so. The idea here is both systems have a highly complex, chaotic, or whatever dynamical behavior. And sometimes those systems, they are not in equilibrium in a case that they have a fixed point, but there might be some limit cycles. Even if they are unstable, they sometimes attract the dynamics, so the dynamics becomes predictable. And then we are interested in, if we observe this in one system, is it reflected in the other system? So that means we really look with a scalpel, or if there's some sort of exchange between both systems. So that's like in the top right, you see just a figure of an oscillator. And when we run the analysis, we get essentially one leading mode that says, okay, it's this red one that says, this is the principal behavior of the system. The system is characterized by this, and it's then reflected in a pair of, like, you know it maybe from Fourier analysis, sine and cosine. It's a pair of eigenvalues. I could spend hours just talking about this method. If you're interested in it in more details, there's a review from Michael and colleagues. And if you're also especially interested in this idea of synchronization and coupled modes and so on, there's two other publications that is interesting that just introduce this method for the synchronization analysis in 2011. And there was interesting application to the synchronization of world business cycle behavior just released 2 years ago. And of course, on the website of our group, you can find a lot of practical details. Once you say, okay, I want to extract something, because that's not what we focus on. Do we find some cyclical components that are shared by both? Is there an exchange of information between both systems? But just the presence of cyclicity doesn't mean that this is real, that it can be spurious. So a good hypothesis test is very important here, that to test if the significance of what we are looking at. So here we use what is very classical. We fit autoregressive process of order 1, which has a kind of, it's sometimes called red noise, to each of the time series, and then we look if there's more energy in the observed system than we can explain by this simple random process. And then on the right-hand side, you see on the top the extracted spectral components, those little dots, the eigenvalues. And if they lie above a certain significance level, that means they are not compatible with the hypothesis. So we must reject that there are two independent systems that do not oscillate. So there must be something more in it. And on the bottom, it's just an example. You see the kind of reconstruction of this oscillation in time. So it's somewhat similar to Fourier, but more advanced. So let's come to the results. First, we are just interested, okay, is there any interannual variability in the agriculture sector in those countries that is shared between those countries? Can the countries be considered as an entity, or is there a strong diversity? So on the left, you see on those 6 panels, the 6 countries that we had considered, and you see a very rich spectrum. So they all have different spectral components. It's no picture is identical to another one. But you see there's a few black dots, oscillations that peak out or that are above a significance level that can, and there we must assume that there's more recurrent oscillatory behavior that can be explained by random behavior. And you see sometimes those vertical lines, they are shared between different countries, like the blue 4.8 here. But there's also a lot of strong diversity between all the countries. That means it's not just a single system that you can aggregate to one system. You really have to see that there's particularities. And this, actually in this test, we have removed what is called a composite hypothesis. That means we do not detrend the time series. We just when we estimate the process, we can say, okay, we don't consider this part, but we do not detrend. This is very important. These are not just spurious effects of a detrending. The trend, so these are really fluctuations that are small, but that are on top of the long-term trend. As I mentioned on the right, this strong diversity is somewhat in contrast to what we have observed, for example, in Europe, where the countries are much more share more of those modes, so they are more strongly related to each other. And so we also checked this with other countries like the US and France to see if there's some external drivers or something that can be attributed. But to our surprise, we couldn't find any coupling between those and the modes we found here. So that might be that the coupling is much more complicated or even not so visible here. On the other hand, our climate, so it's another separate analysis before we merge together. This is just our climate indicators. That means rainfall, temperature, and as a large-scale driver, the Southern Oscillation Index, which is always good to have into mind that there's global large-scale drivers that might be responsible for what we observe in a certain region. So it's not a surprise then we see that on the right panel figure that we can identify well-known periods which can be linked to quasi-quadrennial and quasi-biennial oscillations, which are well-known in other ENSO or El Niño Southern Oscillation indices. And they are also reflected, of course, then in rainfall and in temperature in this region. But beside of those two red and what is orange vertical lines, we see there's also other things going around that cannot be linked at least to this. And now we were wondering, okay, those modes that we identify in the agriculture and in the rainfall and temperature, are they linked? Can they share something? In this study, we have chosen to split the analysis to separate countries because we first tried to merge everything into a single analysis, but this was, because of the diversity, there was not a clear picture coming out. And so I'm going to show you 3 slides on separate country analysis because each country has its peculiarities. Okay, I'm very good in time, I think. So let's first show some results on Senegal. On the top right, you can see the 2 spectra of the agriculture and the rainfall. And there's one common dynamical mode or one oscillatory mode that sticks out at around something like 5 years. This is the only mode that is shared between both. So if we reconstruct the dynamics of, from this mode. That is shown on the left. On top, you see the agriculture. The black curve are the trend residuals. The residuals when you remove long-term trends. And superimposed on it, you see the red. It's a reconstruction with this special mode that we found coupled between both systems. And it indeed gives a very good approximation, the red curve of the black curve. And we see that this mode explains something like a third of the variance that we have in the trend residuals. And on the bottom, you see the corresponding rainfall. We only found this coupled to the rainfall, not to the temperature. And in the temperature, in the rainfall, you again see that, especially at the second half, it gives a very good approximation of the rainfall in this region, and it explains a quarter of the total variability. And now, what does it mean? What can we learn from this kind of analysis? Because we are looking just to a single mode. We didn't do any just correlation, but we really looked for a couple, or for just the frequency. As I mentioned, both modes explain a lot of variance in the residuals, and in absolute amplitude, the agriculture, it's a mode that has an amplitude of something like 170 million US dollar up and down. On the bottom, the rainfall, it's something like 6 millimeter of rainfall per year. That mode goes up and down. That means variation of rainfall in just 6 millimeter per year can be translated into something like a value, something like 170 million US dollars. So what is important, it's the ratio, it's not the absolute value. So you can from this mode, you can translate from changes in rainfall, which might be because the rain belt, sometimes it's going further north, sometimes it's less going north. And so you can translate what concrete variation in rainfall variability, how you can translate this into concrete values in agriculture. The same we also did for Niger. Niger actually it's a country that is further north, so it's exposed to much lower rainfall. And so it's at no surprise that on the bottom you see in the rainfall, it's just 1.5 millimeter variation. It translates to even much higher value in the agriculture, like quarter billion US dollar. And so it really reflects higher exposure to risks, to small variations in the position. And then just yet another case study here in Sudan. We found actually it's interesting that here the temperature has strong impact on the, not only on the agriculture, but also on the GDP. Because actually I didn't mention, in the two other countries we couldn't find this coupled to GDP, just to agriculture alone. But in Sudan the temperature has a strong impact on agriculture and then of course also on the GDP. And here it's a phase opposite behavior. That means an increase in temperature by something like 0.5 degree translates into a decrease of agriculture by $500 million US dollar. So it's again a very strong effect. And the idea why we actually did this analysis, we didn't look to long-term trends and look how this translates into long-term GDP or agriculture. We really looked like a physicist, like you have two systems and you slightly perturb one system and you look to the response function. And that's the way how to look to the response function of the economic with respect to small fluctuations in the climatic drivers. So, and then to conclude it, there's of course a very strong locality and diversity in this region, so it's not no country behaves like another. It's very complex setting, especially it depends on where you are, how strong you are exposed to the rainfall. And since those countries have the GDP has or the agriculture has an extremely high share on the GDP, these countries are very exposed to small climate variations. And as I mentioned, this is a result of a work, and if you're interested, there's a related publication to it that appeared in Ecological Economics. I think I'm done. Thank you for your attention.
Fascinating. Thanks, Andreas. Questions, folks? Switch that one on. Matt.
I'm not sure I understood the mathematics of it, sorry, but the implications are possibly pretty profound. Have you looked at locations or countries where irrigation is a main driver for agricultural impact, and whether your assessments would hold? Is it the fact that there is so little irrigation that you're able to find these close coupling with the output and the rainfall?
You mean irrigation versus no irrigation technologies?
Yeah.
No, we didn't try to separate between. It's of course an interesting question, but we always try to find for developed countries, and of course then you don't find those imprints of you don't find climate signal just in agriculture in very developed countries. But it might be of course interesting to see if it really depends on the on the technology of irrigation, on the quality of the technologies, I mean.
Well, I wonder if you, like in places like Australia, you'll see a much bigger long-term effect down the track, where you're using irrigation, but then you get a millennial drought and everything collapses.
Yeah.
That's a cheery thought. Yeah. Okay. More questions, folks? You having that post-lunch digestion moment? Well, I thought it was really fast. Michael, quick, yeah, you get the last word.
First of all, this was essentially the product of an internship of a few months by Vivien Sanfargarneau. So, this is not a long-term research program, okay? And the real motivation was that this clearly is a crux of interaction between, socioeconomic and geoscientific problems. I mean, remember that on a different day we talked about the biogeophysical feedback of Jules Charney, and so it was very interesting. I mean, the two very interesting results were that it's not a homogeneous region, that there is a substantial impact of climate on the economy, and that it is, at least at this level, not driven by the obvious economic interference of major economies from elsewhere. Okay?
Can I? That's a good point, Michael. Can I ask Andreas? I mean, Sol, Xiang, and others published this paper on tropical economics, quite well cited, with cruder methods, but econometric methods showing that there is this really strong correlation between climate variability and agricultural production throughout the tropics. Do you see anything? Are you essentially supporting their results, or with this kind of heterogeneity, are you suggesting there's something different going on?
Yeah. I'm actually not aware of this.
Oh, okay, then I should shut up and I'll send. But it's called. There's a Xiang's paper on it's just called Tropical Economics, and it uses classic econometric lagged regressions, also shows a very strong effect of climate variability on both agricultural production and GDP across countries throughout the tropics. So very consistent, I think. Great. Okay. Let's thank Andreas.